Hi, welcome to what will be the final video for the first topic of Year 11 Chemistry. This is subtopic 1.3. This is on quantities of atoms. So, for this one, I'm going to introduce you to the concept of what we call the mole. So the mole is a unit of measurement in chemistry. It's how we can use things which have different masses and give them a relative way that they will react together. So in chemistry, the mole is 6.02 by 10 to the 23 atoms or molecules, and that's what's called as Avogadro's number or Avogadro's constant. All right. So it doesn't matter what you've got, if it's 1 mole of carbon atoms, or if it's 1 mole of sugar, or if it's 1 mole of carbon dioxide, or if it's 1 mole of oxygen gas. No matter what we're talking about, 1 mole of those has 6.02 by 10 to the 23 particles. Okay. 1 mole of each atom is equal to its mass number on the periodic table. Okay, so if you're looking at carbon and you see that it has a mass number of 12.01 grams, that means 1 mole of carbon is 12.01 grams. If you look at oxygen, for example, though, you'll see its molar mass is 15.999. So 1 mole of oxygen weighs 15.999 grams. Okay, so here's just a bit of an example of trying to show each of these different parts. So 1 mole, 6.02 by 10 to the 23, whether it's water or lead or sodium chloride, so salt or helium gas, or this one's aspirin or sodium, doesn't really matter, right? 1 mole of each of those, all right, has this many particles, but they all weigh a different amount. So water is 18 grams, whereas sodium is 23 grams, whereas 1 mole of lead is 207 grams. Okay, so they have very different masses, but they are all equal. They all have 6.02 by 10 to the 23 particles. All right, go into a bit more depth here if you need a bit more explanation and get your head around this. Important as we go into this concept that you've got an idea of scientific notation. So if you struggle with scientific notation, you might just want to quickly have a look at this video on my website around scientific notation, because quite often when we're using this, we have very big numbers or we have very small numbers, so you need to be able to use scientific notation. All right, so molar mass is the mass of 1 mole of a substance. So we give it a capital symbol M, and the units are grams per mole. We find the molar mass by adding up all the mass numbers of each of the atoms in a formula. So sodium chloride is NaCl. It consists of 1 sodium atom, 1 chlorine atom. So you look at the masses, the atomic masses from the periodic table, and sodium has a mass number of 22.999. Chlorine has a mass number of 35.45. So because the formula is NaCl, we add those together and we get 59.449 grams per mole. So 1 mole of sodium chloride will weigh 59.5 grams. Sulfuric acid, H2SO4, has 2 hydrogens, 1 sulfur, and 4 oxygens. So again, you find the atomic masses off of the periodic table. So hydrogens 1.008, sulfur is 32.06, oxygens almost 16. Then we just multiply by how many there are in the formula, and we end up with a total atomic mass of 98.076 grams per mole for sulfuric acid. So have a look at this video if that wasn't straightforward for you, but hopefully it's a reasonably simple concept. You just add up the atomic masses off the periodic table and work out the overall molar mass of the substance. Then we use this first stoichiometry calculation. Stoichiometry is the term we give to calculations in chemistry involving mass or volume or concentration. And so I help my students remember this by saying that number of moles, N, is birds flying over mountains. So if you're really, really horrible at drawing like I am, okay, this is how, if someone asked me to draw birds, I would draw birds. So I'd draw them like that, you know, so it looks a bit like an M, and then you've got mountains, all right? So you've got birds flying over mountains. That's how I tell my students to remember. This triangle here is really, really good and important, all right, because this allows you to work out either number of moles or mass using the formula. So if you're looking at using number of moles here, number of moles is mass divided by molar mass. If you're looking at calculating mass, it's number of moles times molar mass because they're next to each other. So this triangle is really, really useful for you to use. So I'll show an example of how we calculate the number of moles. So how many moles are in 20 grams of sodium chloride? Well, we worked out the molar mass of sodium chloride back a couple of slides ago. All right, and we know the mass here is 20 grams. So we simply do number of moles is birds over mountains. So 20 over 59.449, which is the molar mass, and we get number of moles of 0.342. Okay, again, there's a video here with some more examples if you want to go into this in a little bit more depth. If we're calculating mass though, all right, we use mass equals number of moles times molar mass using that triangle that we had a couple of slides ago. So we've got what mass of sulfuric acid is required to make 10 moles. Well, we have 10 as our N value. The molar mass is 98.076. Again, we worked that out a couple of slides ago. We simply multiply them together, and we would need 980.076 grams of sulfuric acid to make 10 moles. All right, again, more examples over here. If we want to know what the actual formula of a substance is, we can do that using what's called percentage composition. So what you need to do to understand that is to have an understanding of what the difference between empirical and molecular formula is. So empirical formula is the simplest whole number ratio, whereas molecular formula is the actual number and type of atoms. So I always use glucose as an example here. Glucose, most people know, is C6H12O6, or commonly known as sugar. That's what the molecular formula is. So we have 6 carbon atoms, 12 hydrogens, and 6 oxygen in every glucose molecule. However, the ratio of 6-12-6 is actually 1 to 2 to 1. So if we were to say the empirical formula of glucose, it's CH2O. So empirical formula is just the simplest whole number ratio, whereas molecular formula is the actual formula of the molecule. Okay. So if we want to calculate what the empirical formula is, we need to know the percentage of something. So if we had a substance, we knew that was magnesium and oxygen, and we found that it contains 60% magnesium and 40% oxygen, we could work out what the formula is. So to do that, assume there's 100 grams because it's percentage, and because 60% of it is magnesium, 60 grams of it must be magnesium and 40 grams must be oxygen. Now you're just trying to work out the ratio. So you take the molar mass of magnesium from the periodic table, which I've just rounded to whole numbers here, but it's pretty much close to 24. So the 60 grams divided by the molar mass, which is 24, gives us 2.5. If you take oxygen, you take that 40 grams of oxygen from here, and you divide it by the molar mass, or the mass of oxygen off the periodic table, which is 16. Again, you get 2.5. Because the numbers are the same, 2.5 and 2.5, you end up with a 1-to-1 ratio. So the empirical formula is MgO. Okay, the ratio of magnesium to oxygen is 1-to-1. Okay, the reason that it's not 50% magnesium, 50% oxygen is because magnesium and oxygen have different masses. Okay, magnesium's heavier. Magnesium weighs 24 grams per mole, whereas oxygen is only 16 grams per mole. So we have 50% more magnesium in there by mass, but the actual ratio is 1-to-1. Again, there's a video here on calculating empirical formula if you want to go through this in a bit more depth. If we step it up to go a bit harder, all right, if you want to actually calculate now the molecular formula, you need to do empirical formula firstly, and then you need to work out, you need to know what the actual molar mass of the substance is. So if we've got a substance which has 35% nitrogen, 5% hydrogen, and 60% oxygen, we just go through and work out the ratios as we do normally here. Now, when you work out these ratios, you get 2.5, 5, and 3.75. So the first thing I always say to people is take the lowest number, which is 2.5, and divide everything by it. So 2.5 divided by 5, I'm just going to write on this actually to show you what I'm going to do. So we're going to divide this by 2.5. And again, sorry, writing with my touchpad is a bit more difficult. Okay, so we're going to divide that by 2.5. We're going to divide this by 2.5. We're going to divide this by 2.5. So when we do that, this is going to give us, there we go. So that's going to equal to 1, okay, which is what I've got here. And then 5 divided by 2.5 will give us 2. And 3.75 divided by 2.5 gives us a value of 1.5. So now we've got a 1 to 2 to 1.5 ratio. Again, this is, again, I said this is a little bit harder. So what you need to do now is you need to get these into whole numbers. So 1.5, to get it to a whole number, that needs to get to 3. So 1.5 times 2 gives you 3. So multiplying everything, we get 1 to 1.5. Okay. All right. Now this says multiply by 1.5, sorry, that should be multiply the 1.5 by 2 to get a whole number ratio. Sorry if that's confusing. So the ratio of nitrogen to hydrogen to oxygen is 2 to 4 to 3, so that's the empirical formula. Okay. Now if you add those up, work out the molar mass of this using the periodic table, 2 times 14, 4 times 1, 3 times 16, we get a value of 80.05. Now up here we were told the molar mass is 160.1. So if the molar mass 160.1 divided by the mass of the empirical formula here gives us 2. So that's telling us that the molecular formula is actually twice the empirical formula. Okay, so this is the simplest whole number ratio, but this is the actual formula of the substance. I'm sorry, I know I haven't explained that too well. I'm getting tired, but hopefully you can follow through the working out I've got here, and you can see sort of from the values we've got how we've ended up with this molecular formula. All right, there's no substitute for practicing in terms of stoichiometry and these ones. Just start off by doing simple ones like calculating your molar masses, calculating number of moles, calculating your mass. Try doing some of the empirical formula and molecular formula ones if you want to. All right, and this one here goes into much more depth. This starts to cover things like concentration and volume calculations as well. So if you want to jump into those, you can, or you can wait for a little bit later. All right, that's all for this first topic. Hopefully these have been helpful. As always, if you've got any questions, just ask. Thanks, guys.